Hello, students. Today we want to talk about continuity. As I've mentioned before, the limiting process is directly connected to the definition of continuity. There's just one subtle change. And so, like I said many times in the previous lectures, is that when a limit exists, that's really a good indication of controlled behavior. That is, if a limit exists as x approaches c, then we saw that in a delta neighborhood of c, we can control the size of the function. So basically, when limits exist, we have a controlled behavior of the function, and that's always good. That means we're working towards really nice functions. Now, before I share with you the formal definition of continuity, I think I said before that I want to give you a theoretical basis for some of the limits that exist in the previous section. And one was that of the limit of sine and the limit of cosine as x approaches zero. And then using some algebraic manipulations, we can actually show that limits for sine and cosine exist for all real numbers, and that the limits can be computed by direct evaluation. And that's really an important construct. Like I said before, remember we said polynomials, rational functions, trigonometric functions, radicals. All of these functions have limits by direct substitution. That is, where we have the direct substitution and a real number resulting, then we have the actual limit. And that has to do quite a bit with continuity. Even though I haven't said it, I'm thinking you're believing in your mind now that these functions must be continuous on the sets where they have limits. And if you're thinking that way, then that's exactly true. So I've sketched out an argument for the sine and the cosine, so I want to share that with you. It looks a little complicated, but it's not. The idea is that this uses the squeeze theorem. And I wanted to write it so you can see the use of the composition result too. So what we do in order to effect a proof with sine and cosine, we really have to go back to where we defined them, and that's unit circle, S1, okay? So what I've done is I've drawn basically the first quadrant here where we consider, let me go ahead and turn off my email so it's not dinging while we're trying to do our lecture. Sorry about that. Let me go back to this. So what we want to do is look at how we can utilize our geometric definitions. And what I was saying is that the angle here denotes the distance along the unit circle. That's basically how we define sine and cosine as x and y coordinates of the unit circle, where the angle or the distance along the unit circle to that terminal point defines the input. And that is quite an elegant definition. It's very geometric oriented, but we're going to see that we can continue to push the envelope and generate other forms of sine and cosine, which could have easily been a way to start the process. But what we find is that when we appeal to geometric objects, we have the beauty of circles, right triangles, and that makes solving particular problems in engineering and science very useful and accessible, so to speak. So here's how we do it. We want to use the squeeze theorem, so we need an inequality, and it's not very difficult. So since we're approaching zero, notice what I've done here is I'm going to let x approach zero from either side. And notice for this particular argument, we're going to look at the right approach where the value of X is actually positive. Okay, so I've denoted X here and it will get smaller and smaller. So in order to get my inequality, what I've done this little red triangle here with the height sine X by definition of sine X. And then we want to think about the corresponding sector. So the sector area is larger than that of the triangle. And then, of course, a lower bound for the angle or for the area of the triangle is 0. Now, how do we do that? Well, what I did over here, I thought I would add in blue before I started my lecture that it might be good to remind you of these, even though I'm sure you remember the first one. The area of the triangle, at least in simple cases, can be done with 1/2 base times height. And the area of the sector is just something we get from the area of a circle, which is 1/2 r squared theta. But remember, for the unit circle, the radius is 1. So when we do the triangle area, we have the base of 1, we have the height sine X, and then, of course, the 1/2 factor. And then for the sector area, we have 1/2 r squared, so 1 squared theta, but theta is just X here. So that's it. 0 is less than or equal to 1/2 sine X is less than or equal to 1/2 X. And then, of course, if you like, you can multiply through by 2. And so that gives us 0 is less than or equal to sine X is less than or equal to X. And notice for this particular quadrant, even though I maybe was a little bit large here, I could have done like maybe pi over 4, but 0 to pi over 2, X lives there. So we can see that this value of X lies in this particular open set, and we're allowing X to decrease or converge to 0 from above. And so therefore, by the squeeze theorem, we have now squeezed sine X between 0 and X. But these are easy limits to compute. The limit as X approaches 0 from the right of 0 is clearly 0. And then the limit as X approaches 0 from the right of X is just direct substitution. So let me write that in. I just repeated the value of X. So that would just be substitution of 0 for X, and that gives you 0. So now, again, even though I haven't formally defined limits from the right and left, you know what they are. It's just restricting the approach. So we approach from the right or we approach from the left, and then that's making us think that if we do that for the standard limit to exist, as we thought of in the past, both the left and the right limit must exist and they must be equal. And so there are times when maybe the set doesn't allow us to approach from the left or the right, and we just have a single approach. So right and left limits are definitely useful and certainly needed. So since the limit is not X, obviously, it's X evaluated at 0, we get 0. So now we have the outer limits here equal to 0. So by the squeeze theorem, that forces the function squeezed in between to have the same limit. And that's an elegant application of the squeeze theorem. So you're thinking, okay, well, that's not so bad. And what I did here, I simplified this argument for the other case just to make it a little bit easier. So now just think, if we're going to now move less than 0, that is, we're going to approach 0 through negative numbers. So what I've done here is just take X in the interval negative pi over 2 to 0. But of course, applying the additive inverse, that will just put the additive inverse of X in the previous interval here. So I thought it would just be easier to use the first case instead of being more elaborate and maybe not necessarily efficient. So now, if X is approaching 0 from the left, for sine X, we can simply replace X with its additive inverse in both cases. And so now negative X is approaching 0 from above because of this. And then that's just the first case. So sometimes if you like, you don't want to write negatives here, you can just replace negative X with alpha and make it look nicer, but it's not required. So this is just the first case which we've done, so that's clearly zero. So many times in mathematics, we reduce to a previous case and do a lot of work in the first case or the previous case and then apply that to other cases without having to reinvent the entire argument. And that's exactly what I was doing here. So now when you see this, you have approach to zero from the right and approach to zero from the left, and the limits in both cases are the same. They're both zero. So now this means that the standard limit, that is the limit as x approaches zero of sine x, is actually zero. And now we want to observe that, again, that's kind of direct substitution. Sine of zero is zero. Okay, so the idea is we're trying to push that result for all real numbers. We know that by our definition of sine and cosine, that those two functions are defined for all real numbers. Now, what I want to use, as you note over here, is the composition result. And the easiest thing to do is to now just simply say, okay, if we've got this limit here, we've got this standard limit, does that give us the limit for the cosine as x approaches zero without having to break up into left and right? Well, it actually does. So I wrote here identity by just using the principal square root of 1 minus sine squared x, which is a replacement for cosine x, as long as we're approaching zero. You know, that would be via the first and the fourth quadrants where the cosine is positive. So this identity would certainly apply. Now, I added an extra step over here because I went from here to here kind of fast. But this is the composition result. So now we can just move the limiting process inside by the composition result. And now, of course, we've got the limit of 1 minus sine squared x. But we know the limit of sine, so we can just move the limiting process inside the square. And that's what I did here because I just jumped to it right here and I thought, well, that might be a little bit unclear. And so now this limit we have right here. That is the limit of sine x as x approaches zero, we proved here, and that's actually zero, or sine of zero, as I've written here. Of course, the limit of 1, a constant, is just 1, so we have 1 minus 0 square root, which is just 1. Okay, so the limit for the cosine as x approaches 0 is simple if we use the composition result and the result that the limit as x approaches 0 of sine x is 0. So now what we see is that we have the 1 that we thought was correct, but then, of course, that's just direct substitution if we bother to mention that, okay? So the key to doing the limit result for sine and cosine is computing these first. So this requires a little bit more application of the more fundamental results. But again, remember that we only have what we know, okay? What's interesting about calculus is that we want to keep our arguments as rigorous as we can, but if we start to introduce certain transcendental functions, we only have how we actually created them. And so when you get more sophisticated results for sine and cosine, you can think of them very differently. But I often tell my students that we would certainly be struggling in many problems. And again, like I said before, engineering and science, if we didn't have that geometric interpretation of sine and cosine. So now what I have, move this, I've got a little half sheet here, and then I, kind of spill the beans at the end. And I thought, what's the simplest way to take the two limits that we just computed is to use this argument. So here, notice I've written the definition of continuity, but for now, don't worry about that. I'm not gonna say much about that, except that you can see that it's just a limit definition, but I'll say more in a few minutes. Now, to get the result that we can compute limits of sine x as x approaches c for any real number, we're going to cover. And then, of course, by a similar calculation, as I've written down here, we can do the same for cosine. Now, notice if we fix a c in R, that is some real number, and set x equal to c plus h, we can look at the following limiting construct. That is, if x is approaching c, then analogously, h is approaching 0. That is, if h is converging to 0, then we simultaneously see that x is approaching c. So we have an equivalence here. This allows us to be able to toggle between these two approaches. And so that gives us a mechanism to use an identity for the sine function. So again, like I said before, we have to use what we know. We have to use the mathematics that we've created for these functions. So we can't just make up new stuff that we don't have any understanding of. So now, if you look here, the limit of sine x as x approaches c will now be the limit as h approaches 0 of the replacement here, sine of c plus h. Okay, so the mechanism works by this toggle right here. Now, of course, we do have what we call addition formulas, which we will use in this class. Of course, I got to move around to keep the lights from going off. We'll use in this class, and then even more so in calculus 2. So, of course, sine of c plus h is just an addition formula. So that's sine of c cosine h plus sine h cosine c. Now, this is where, like we had last week, I mentioned some of the limit theorems in the more general realm, where we have the limit of a sum is the sum of limits, as long as those individual limits exist. And then, of course, we can factor constants. So now you can see that the limit of the sum is the sum of limits. But if you notice here, let me find my red pen. Sine of c, that's a constant. That's fixed. Cosine c is a constant. So this is fixed. Because c is fixed. That's a number. So what I've done here in the second step is simply factored the constants and left the varying quantities to the right of the limit sign. So now we're like, okay, well, that's nice. The h approaching 0 is why this works, because that's what we know about. So now, of course, the limit of cosine h as h approaches 0 is 1, and the limit of sine h as h approaches 0 is 0. Okay, so that zeros that term, but we're left with 1 times sine c, which is sine c. So now you see that the limit as x approaches c for any real number of sine x is just sine of c. So this again is direct evaluation. And there has to be something that is important about that. Okay, we know that certain limits require more work, especially when we have indeterminacy. But when we have limits that we can compute via direct substitution, that's much simpler. So now I just kind of let the cat out of the bag, and you'll know why just in a few minutes. I'm going to share with you some of the components of continuity. As I said later here, in just a few minutes, sine x will be continuous for all real numbers, and likewise, by a similar argument, we could do the same thing. Cosine x is continuous on R. So for all x. So what is that definition of continuity that now will allow us to use this direct substitution for these limits? For instance, we have that result. How does that meld with continuity? So let's look at that. So this is where I have some of the basic definitions. So notice here what I've written is direct connection to definition of limit. And then, of course, we'll say a little bit more about right and left limits, but I think you already understand what they are. You're forced to talk about them because you have no choice. So now just again, using the same terminology I've had before, we're going to fix C element of R, and then we're going to say F is continuous at C. And then I want you to look at what I've written here and see that it's basically, except for a couple of adjustments, the definition of limit. Notice we take any epsilon, we take an epsilon positive, and then there exists a delta, such that if X is within delta of C, then F of X is within epsilon of F of C. So what's the key difference here? What's the key difference? The key is that F is defined at C. It has to be, and it has taken the place of L. So before, this quantity was just L. So we see that L equals F of C. And because that's true, we don't have to restrict X from ever equaling C. So we don't have the greater than 0 here. So that inequality is missing. So with just two minor adjustments, we get the definition of continuity. So when I said that the limit definition is important, or the fact that a limit exists is actually a good quality for a function to have, I meant that. So now you're thinking, what could we do? I mean, the epsilon delta definition is fine. Is there an adjustment or an equivalency of that might be easier to remember? Because again, we're thinking we want to tie this back to these limit results. So equivalently, F is continuous at C if and only if, and it's just written right here. The limit as X approaches C is L, but L is F of C. So I've written useful characterization. So basically what we're seeing is that if we can compute a limit by direct substitution, which is exactly what this is saying, and here's another way of characterizing this. When we say the limit as X approaches C of F of X, we're moving the limiting process inside. Limit as X approaches C, just like the limit result of a, let me not write the C yet. The limit result for a composition. So basically what's happening is that we're moving the limiting process inside, just like we're doing the limit of a composition. And this clearly is F of C. So this characterization of continuity is extremely useful. So again, now we can see that all the limits that were computed thinking about domains of functions by direct substitution means now that we have continuity at those points. So we can evaluate sine and cosine limits by direct evaluation. And then of course the others, trig functions, tangent, cotangent, secant, cosecant, they are certainly manifestations of sine and cosine. For instance, tangent being sine over cosine. So the idea, if we know the results for sine and cosine, we automatically get the results for the other four trig functions, basically saying, okay, these functions have limits where they're defined, and therefore they are continuous where they are defined. So that makes the result of continuity for many of the functions that we've studied for quite a while very simple. Again, trig functions, radicals, polynomials, rational functions are continuous where they're defined, because when we compute limits on their domains, we compute them by direct substitution. And the direct substitution is now, by definition, giving us continuity. So when you think about the fact that the limit exists, you've got this kind of approach the function actually approaching a specific number, and now things join. We don't necessarily have a hole at C. We now basically see that it's the function defined that way. So that keeps the function from being erratic. Basically, when you think about it, the function has many good qualities, that it's bounded and of course can have no gaps. If you have an interval on which the function is continuous, then there won't be breaks in the function. There won't be holes in the function. That would be impossible. Because that would violate this. So the amazing thing about this definition and what we enjoy by it is that it is so clean and so effective mathematically that it's amazing. We're doing limits and thinking that, you know, continuity is going to be just a far cry from the limits, but it's basically utilizing the limit definition with a few adjustments that make the function even better. So continuity takes the limit and improves it somewhat. So having the existence of a limit at C is great, and then even improve it by having the existence of continuity. So now, one thing I want to say here, just to get us started with some of the examples that we want to do. First, we just need to make sure we have the basic foundation here. If we have continuity basically for a point, how do we get continuity on an interval? Well, it's very simple. Let's just look at this. It's quite simple and it makes perfect sense. So let's just take an interval. We'll take fix A and B, A less than B, and we're going to say that the function f is continuous on the open set if and only if, okay? For any C in the open set, f is continuous there. So that just means that we can always compute limits this way. So when you talk about an open set, you're simply saying that the definition of continuity is satisfied for every C in the open set. So you just extend it to all the points in the set via this definition. That's it. So if we have continuity on a set, we have a really nice function. That is, some students will say that means that if I were to sketch the graph of the function on that interval, again, like I said before, there are no holes, there can't be, there are no gaps. The function cannot become infinite because of the existence of limits, which we've already shown. So you don't have to just focus on thinking about functions via a graph. I mean, if you understand the calculus of the function up into this point, then you know what to expect with the graph. And then, of course, there will be other attributes that the graph and the function will have. And so then we will be able to actually produce the graph with a great deal of accuracy. So again, what's important, and as you thought about in college algebra and pre-calculus, is that by understanding the function, you understand its qualities. And because you have that understanding, then you can provide a sketch of the function. So what we want to be able to do is to learn enough about the qualities of functions through calculus so that our understanding of the function is improved. And we're already seeing that we're noticing improvements, and we will see that throughout Calculus 1. Now, how do we consider the closed set? Well, that's a very tiny adjustment. So if we close the set, we include the endpoints, then all we have to do is do the left and right limits. Okay, so if we've got the left endpoint, then we have to be able to approach from the right and just get function evaluation, f of a. So as x approaches a from the right, the function limit is just f of a, direct evaluation. And then, of course, for the right limit, we do the same thing. That is, as we approach from the left, we just get direct evaluation, f of b. Okay, that's it. That's all we have to do. So just to reiterate, as I said before, if a standard limit exists and is equal to L, it's only because of this. That is, the right and the left limits exist and they both are equal. So that is exactly why the definition of continuity provides for a well-behaved function. So when we think about a curve that is continuous, if you think about a curve being represented by a function, it doesn't mean that the curve is necessarily smooth in the sense that maybe it has some rough spots or whatever, but it never breaks. Okay. You never get to a gap. You never get to a hole or anything like that. But it may not be as smooth as you like. And we can't get smooth until we move into the idea of differentiable or derivative. So continuity is very important, and extremely well-behaved functions are continuous. They have to be. Now, when we want to improve the quality of the curve, then we will have to add some other attributes, and that will come shortly. Now, what I want to do is just, before I do some examples, I want to just focus on some basic ideas, like I've said before. I've reiterated the fact, and we can actually call this the continuity theorem if you want. The following functions are continuous at every point in their domains, as I've said many times: polynomials, rational functions, radicals, trigonometric functions. So when you are doing a proof or you're analyzing something and you need continuity, you can always say, well, the continuity theorem states that these functions are continuous where they are defined. That we know from our work with limits, and then just by stating the definition of continuity and applying it to intervals, we're done. We have that result. So that can just be like continuity theorem. Now, what's nice about this is that we can take algebraic combinations of continuous functions, just like we have the algebraic combinations of or the limit theorems. The limit of the product is the product of limits. Okay, so now what you can do is you can take two functions that are continuous at C, and then by virtue of that, you get the constant multiple function is continuous at C. Sums and differences of f and g are also continuous. These proofs are so simple. The last proof we did with the squeeze theorem makes this look trivial, and it is, because we're using the power of the proofs from the limit theorems, which are difficult. If you looked in the notes, the product rule proof is challenging. It's straightforward, but it's long-winded, kind of like your professor. So again, the product of continuous functions is continuous. The quotient, as long as it's well defined, that is g of c is not equal to 0, we again get the direct substitution result. So now what we're saying is that we can take all of these functions that have overlapping domains, we can add them, we can multiply them, we can divide them, we can subtract them, we can multiply them by constants and still get a continuous function. We just have to be careful that we use the intersection of the domains. Okay, so we can't have one function having continuity at a point that's not shared by the other one. So just like you did domains in college algebra, when you start combining functions, you have to look at the intersection of all of the domains, and that set will give you the domain. And now it will now give us the set of continuity. So that's really interesting in and of itself. Now, this very last result is really what we already know. It's just the limit of a composition. So what you can see here is we just simply replace the L in the limit result with G of C. So again, if a function G is continuous at C and F is continuous at G of C, then the composition is continuous at C. And so again, you're basically just running the limit process inside to the inner function like we did before with the limit and taking the outer function of that value. So there's no change. We simply now, instead of just saying that the limit of G is L as X approaches C, we just say the limit is G of C. Okay, so because it's continuous there. So the proof is trivial. It's just a direct application of the limit result. So we get all of this stuff for free. All of the work that we did with limits, even though that kind of gets clouded by working with the algebra and the indeterminate forms, all of that work has now paved the way for continuity. So we can just pat ourselves on the back knowing that work now gives us a standard for continuity. Now what we want to do is look at some examples. I have several here. And the first one has to do with the greatest integer function. And I even did part of a graph here. I thought this was kind of an interesting function from your homework. What's interesting about what Dr. Larson does in the book is that he describes the greatest integer function, and it's sometimes called the floor function, as I've written up here. And we don't spend a great amount of time with it. It's just that he introduces it in the book, and so I thought, well, we'll just go ahead and do it. Well, let me define what it is. The greatest integer function for any real number is denoted, usually it's like a script box around it, and this varies so much. Sometimes it just has the little pieces at the end here and not at the top. So it varies, unfortunately, not a universal notation. But in the book, this is very close to what it is. They usually boldface part of the box, but I'm not doing that. I'm just basically putting X in brackets. And the greatest integer function of X will be n, where n is an integer, and it is the greatest integer such that n is less than or equal to X. Okay, so if you think about that, if we had the greatest integer function of 3 1/2, that would be 3. Because 3 is the greatest integer less than or equal to 3 1/2. Very simple. And then, of course, if X is an integer, that's the answer. I mean, that's easy. This is maybe not so interesting the first time you see it. The greatest integer function of 0, of course, is just 0. And then, of course, say we have negative 4.5. Well, the greatest integer less than or equal to this, of course, is just negative 5. So the idea is that we don't have anything that's overly difficult here. This function has a lot of nice applications, and if you do business and finance, you may or take a little detour into some of those classes. You'll use this function more. But what I wanted to do was talk about where the function is actually continuous. So when we think about continuous functions, we want to know if there are points where the continuity doesn't hold, okay? And then we could say, well, if it's discontinuous here, then everywhere else it is continuous. So we can think of a set of continuity for a function, and we can think of a set of discontinuity. Well, we basically list the set that contains the real values for which the function doesn't have continuity, or we can flip it and just say, write the set where the function has continuity. So if you state one, you automatically know the other. So that's not very complicated. So these I looked at from your homework. For instance, here it says, take the limit as x approaches 3 of the function 6x minus the greatest integer function of x. Okay, well, what do? You keep your fingers crossed and you just say, all right, well, the limit of a difference is the difference of limits, and you just keep trucking until you get to an answer, or it just blows up and it doesn't have a limit. So now we have the limit as x approaches 3 from the right of 6x. Well, that's just a polynomial, so that's easy. That's direct substitution. But now, if x is approaching 3 here from the right, so you can say 3, and then you've got the approach this way. So basically, you just have numbers bigger than 3, but close to 3. So when you think about the limits, you're thinking of getting arbitrarily close to the particular value. And so, of course, the floor of this, or the greatest integer function here, in this case, where x is approaching 3 from the right, would clearly be 3 if you think about what we just did in this example here. And so 18 minus 3 is 15, and we're done. So the greatest integer function is kind of fun. Now, what I did in this next example, and I drew a picture here and did some sketches here just to show you how you can work through some of these things. These examples are not overly difficult. You're just going to now have to think about approaching from left and right, because some of the approaches will be obvious. And then there'll be cases when you've got to look at both approaches in order to answer the question. So now we look at this particular function. F of x is 1/2 times the greatest integer function of x plus 2. Okay, we want the set of discontinuities. Well, this is not difficult. We know that x and 2, either together I've written as a linear polynomial, that's continuous. Polynomials are continuous for all real numbers. So, because they're defined for all real numbers. So we don't even have to worry about that. So now what we do is we look at the greatest integer function. Now, what I've done is observe, and I make a statement here, and then I prove it. Okay, so when we look at this, I say observe the greatest integer function is discontinuous for any beta such that beta is an integer. And of course, this z is the set of integers. All right, that's the notation that you use for integers. It's commonplace in mathematics, and we need to know it. Kind of like R for real numbers, and the script N for natural numbers, and the script Q for rational numbers, for quotients. So, and of course, the C script for complex numbers, that includes the imaginary numbers. So now, if we think about this with the last example here, it's very clear. If we let b or beta be an integer and we approach from the right, just like we were thinking about here, then we know that the limit is beta. Okay, well, if we approach from the left, so we're somewhere over here, then all the bets are off, because now the greatest integer function limit here will be beta minus 1. We don't have any choice in the matter, because of the definition of greatest integer function. And then actually what you're seeing now, this becomes a step function. There are gaps in it. So now we see that even though the left and the right limits exist, they're not equal. So this implies the standard limit does not exist. And so, since the greatest integer function is not continuous at integers, that defines the set of discontinuities for this particular function. Clearly, if the greatest integer function is discontinuous at the integers, 1/2 times that or a multiple of that doesn't change the discontinuity. And so we see now that f of x is discontinuous on the integers, on a set. It has discontinuities. Now, what I did here, I thought this was interesting, because in your homework, they use these computers to sketch the functions, which is really no good. If you're using, you can't use fancy calculators in this class. When you take your test, that's not allowed, because it's doing the work for you. And then, of course, if you've got a fancy, expensive computer algebra calculator, then your brain's not functioning. So what I did here is I just took a piece of this. I just look at 0 to 1, okay? And then I'll look for the jump. But now I think about taking a portion of the domain where I know the greatest integer function is the same. For instance, when I evaluate it, it doesn't change. That's how you analyze the greatest integer function. So I started this way and moved this way. So for instance, if x is between 0 and 1, 0 included, 1 not included, then of course f of 0, we can just see will be just 1/2 times the greatest integer function of 0 plus 0 plus 2. Well, of course, the greatest integer function of 0, we know, we did that one up there, is 0. And so we just get what? 0 plus 2, which is 2. So when I graph here, I've got this. And of course, this is linear, but you know, I still have to work a little bit. Now we're thinking, okay, what's happening as we approach 1, in this case, from the left? So now we're doing something like this. So now this gives us 1/2. Again, we've got go up here, 1/2 the limit as x approaches 1 from the left of the greatest integer function. And then of course, now this is just direct substitution, 1 plus 2. But of course, we're still less than 1. So the greatest integer function here in this limit will just be 0. But of course, by direct substitution, we get a different value here. So now the limit as x approaches 1 from the left is now 3. Okay, so now when we draw this linear function, I mean, it looks like a line because it's linear. We start at 2 and then we end up at 3, but I have a circle here because that's not f of 1. It's only the limit as x approaches 1 from the left. And that's why I wrote these out, because I need to actually be able to talk about these, and I need you to hear what I'm saying. So now you're thinking, okay, we have at least that. So where's the jump? Notice I wrote jump discontinuity. Okay, well, let's look at f of 1, okay? Because the greatest integer function will change. So now we have 1/2 times the greatest integer function of 1 plus 1 plus 2. Well, now the greatest integer function of 1 is indeed 1, because when it's an integer, we just get the said integer. So now we have what? We've got, in this particular case, what did I write here? Oh, that's a 1/2 times 1 is 1/2. Sorry, I put a 2 there. I put a 3, but it's 2. So 1/2. And so 1/2 plus 3 is 3.5. So that defines the gap. So the gap here, excuse me, is just 1/2. And I wrote that jump discontinuity. So when you start graphing this, if you look at the graph in your homework, you've got these segments, and then you've got a gap, and then another segment, and then a gap. And this is how you do this when you do these computations. Okay, you have to look at the intervals. Now, of course, if you've got a fancy Maple or MATLAB, you know, it can just blip, you know, and graph things, you know, in a nanosecond or whatever, you know, or 1/1000th of that. And so what I want you to be able to do is note that just as we've done here, we know the discontinuities of f are at the integers, but this gives us some understanding of what the graph will look like. Not even knowing anything except limits and continuity. We're looking at the fact that if a function's going to be smooth, is that going to be an improvement to continuity? We're thinking probably, I mean, smooth is going to be something that might be just a little bit better than the continuity. But clearly here, this is at the integers, this is not continuous. This is not something we can repair. So when we think of classifying discontinuities, this is an excellent example for this, and this is why I'm including it. We can't repair this, okay? You can't just push these together. This is what we call non-removable. So this is a non-removable discontinuity. That is, you can't repair this. For instance, you're thinking that the functions with the holes in them are repairable, and we could call those removable. I'll say more about that. Now, as I said before, I repeated all of this about the continuity theorem, and I was going to call it continuity criterion, but I had to quit that because that has to do with functions and sequences, and we've been doing that. I've been giving you examples where we have a sequence approaching a particular real number, especially showing you when limits didn't exist, okay? So that is a valid technique, but I don't want to confuse it with a result in advanced calculus or just calculus, whatever. So I'm going to call it continuity theorem. So I changed that, and so let's just remember that we've said this many times. Now, what I want to do is look at some examples that are fairly straightforward. Notice here, when I talk about removable discontinuity, that would mean that the left and the right limits as x approach c would have to be the same. Okay, they both have to exist and be the same because we would have to have the function doing something like this as x approaches c from either side, no gap. And then we can define f at c by the limit to, like, boom, fill in the hole, so to speak. So if we have the left and right limits equal, then that helps us decide how we can define the continuous function. Now, let me just skip over here, and I'm going to show you a simple example before I go over these. Look at our friend here. Here's an example of this. As I was writing these examples up, I thought, well, let's just go back to this special limit. Well, I say check x equals 0 because clearly this is not defined as 0, but we know this special limit. The limit of sine x over x as x approaches 0 is 1. If you look in the notes, I applied the squeeze theorem to the last example that we did, or the first example, to show continuity for sine and cosine by using that theorem to get the limit as x approaches 0 of sine x is indeed sine of 0 is 0. So now you can see that we've got this going on just because we know this result. So now we can define the value of f of x, in this case, to be 1 at 0. So g of x, we would call that the continuous extension of f. So removable discontinuity of 0. We can remove it. We just basically color it in by defining the value of the new function to be 1 at x equals 0. And this would be continuous for all real numbers. So the idea of having a removable discontinuity is actually a good thing. I mean, we don't have a lot of problems with that. So I just wanted to mention that since I wrote this here. Now, let's just look at some simple examples. Now, of course, it looks like I went on forever here, but I'll show you why. Here's just a basic college algebra problem. Notice we have a rational function. Rational functions now, by the continuity theorem, are continuous where they are defined. And so now, of course, you look here, and of course, if you factor this, 2 minus x times 2 plus x, you know that the discontinuities are 2 and negative 2. Okay, so the problem here is that in the next lecture, we're going to talk about vertical asymptotes where functions become unbounded. Okay, so these are clearly non-removable if you just think about the work you did in college algebra and pre-calculus. So discontinuities, throw out those two because those are actually where the function becomes unbounded. And we'll say more about that shortly. So that's really simple. Now, what we want to do, and this is a nice WebAssign problem, and I just want to show you the analysis that I did here. It's very simple. It's long, but only because it has to be. Notice we have f of x is a function in pieces. It's x when the absolute value of x is greater than or equal to 1. And if we're in between 1 and negative 1, we have sine of pi x over 2. Okay, well, notice here I say f is clearly continuous if we throw out 1 and minus 1. Why is that? Well, this is a function here that's continuous wherever it's defined. It's just a sine function. And then of course x is a polynomial, so it's continuous wherever it's defined. So the thing is, if you have a function in pieces, you just have to look at the boundaries, so to speak. Where do the pieces change? For instance, where do you go from one piece to the next? That interface, so to speak. And so we want to check 1 and minus 1. So what I've done here is I've written approach from either side, because we don't just have a number here or a constant. So wouldn't have to worry about the value of the limit if it were constant. So basically we look from either side. So we check 1. So here what I've done is I'm approaching 1 in this particular case from the left right here. So in that case, f is defined as sine of pi x over 2. So you just do your limit by direct substitution. So you just replace x with 1, you get sine of pi over 2, that's 1, that's f of 1. Oh, look, that's f of 1. Because f of 1 is 1. Okay, well, good. I put a check, but don't let the cat out of the bag yet. So now we approach from the right. So we have the limit as x approaches 1 from the right of f of x. Well, it's defined to be x there. That's just direct substitution. Well, maybe you could have done that in your head. Okay, so now we're seeing from the approach from the left and the right give us the same value. So the limit as x approaches 1 of f of x is just f of 1, which is 1. So we have continuity for 1 by definition. So notice we obviously got the same thing over here, but let's prove it. Let's try -1, do the same thing here. So now we want to approach -1 from the left. So we're over here. So if that's the case, and again, I think, it's kind of important here if I've done this correctly. So notice here, if we approach -1 from the right, we're over here. And so I need to switch these. Let me show you why. So we'll do plus. Notice when we approach from the right, we're in between 1 and -1, and so that's the sine function. And we approach from the left, we're on this side. So that's important. It flips. It flips between these two. So it's easiest just to do this. So now if we approach -1 from the right, then the function is defined to be sine of pi x over 2. So we just do direct substitution. So we replace x with -1. So we have sine of -pi over 2. Sine being an odd function, you can just factor the negative. We get -1, but that's just f of -1. Good. And now if x is approaching -1 from the left, we're this side. And so that's where f is defined to be x here. So we just have direct substitution. We just get -1. That's f of -1. Now again, the limit as x approaches -1 in this particular case is just f of -1, because we see the left and right limits exist and they're equal. So now, and I don't think this problem is overly difficult, but what I like about it is that if you just draw the disposition of the 2 points that you're considering, and then do your little triangle so you can basically decide, which side are you on, and then go to the definition, then it makes more sense. So of course, when we're on this side, if we approach from the right, we're at this piece. If we approach from the left, we're at this piece. So that's why I had to switch these two. But by definition of continuity, we have continuity at 1 and -1. So now I've just written continuity on all. So these are fun problems, but they're not overly difficult. And I just want to get you used to utilizing the concept of continuity. Good deal. Now, yeah, these concepts are really important. So I've written out a lot of examples because this is an important concept. But it's very straightforward. You just get to use a lot of your knowledge of functional analysis that you prepared in college algebra and pre-calc. Now, of course, we've done the first part. I want to just look at some situations, again, where we think if we can repair a function. So notice here, and this makes this problem a little bit easier. Notice it says compute a element of R such that g of x is continuous on R. Okay, well, notice this is kind of like what I did over here. We have g of x is x squared minus a squared divided by x minus a when x is not equal to a. Of course, we want it to be defined. And then we're going to define the function to be 4 when x is equal to a. Remember, a is a constant, okay? It's fixed. So we want to compute it. Now, first, what we notice is we see that g of a is just 4 by definition. So we need to check a. Like I said before, we have to look at the value of the independent variable when the definition of the function changes. Because now, again, let me just say this, 4 is a continuous function. No problem. It's defined, so anything in this particular case not equal or equal to a is good, but we don't even think of continuity so much in isolation. We can look at continuity at a point, but we always think we can just approach, from either side. So when we look at that, we're thinking we got to rig this so that we have the correct a to make sure that when we do the limit, we do get that number. Okay, so how do we do it? Let's look at it this way. Again, check a. Look at the limit as x approaches a of g of x. And what's nice about this particular problem is that the way it's defined, we don't have to do a right or left approach because it's defined when x is not equal to a. It's not some interval that excludes half of the real number, so to speak. So this doesn't mean that we need left or right here. We just do the standard limit. But of course, this will factor because we have a function with a whole limit. We have the x minus a times the x plus a divided by the x minus a. These absorb. And so we're just left with the limit as x approaches a of x plus a. Direct substitution, a plus a is 2a. Now, again, for continuity, we have to have the limit as x approaches a equal what? G of a. Well, g of a is 4, so the limit is 2a. So then if we divide by 2, we just simply get a is equal to 2. So if we replace, in this case, a with 2, we get x squared minus 4 divided by x minus 4, and that function is continuous on all real numbers. So remember, what's the key? The limit as x approaches a of g of x must equal g of a. That's how we get continuity at a. That's just the definition of continuity at a particular value a. Or sometimes we say point, but just a point on the x-axis. I'm big on terminology. I don't like sometimes that it's abused a lot, but continuity at a means this. And so again, you simply look at the function and think, okay, how is it defined? That again pushes you into how you should analyze things. Now, several of you will often send me WebAssign messages about trig examples, and that's good because you learn your trig, but maybe you don't use it as much and it gets rusty. Now, like I said before, this is a trig function. It says f of x is secant of pi x over 6, continuous where it is defined. Okay, because it's a trig function. We know that by the continuity theorem. Now when you think of a standard period, the period of the secant function is 2 pi, but this is changed because of the coefficient of x is pi over 6. But you don't have to do anything in your head. You just think, okay, these are just intervals of the same length, and so you can just focus on one of them. And that's what I did over here. I looked at pi over 2 to 3 pi over 2. Now, of course, when you define the inverse secant, the way Larson does, we kind of look at this piece, and we'll talk about that in Cal 2. But yeah, when we define inverse trig functions, we want to make sure they're one-to-one. So now we think, okay, how does this coefficient change the what do we want to say, the domain of the function, so to speak? Remember when you do your college algebra and your trig, you can express expand the intervals, you can compress them. That's kind of what's going on here, because if you think about this, look at this. Pi over 6 is a number that's less than 1. So you're thinking you're going to broaden these intervals. You're going to expand them, okay? So using a technique that you learned in college algebra. So now we can just do this using simple math. So we're going to say pi over 2 is less than or equal to pi over 6 times x less than or equal to 3 pi over 2, instead of just doing it piecemeal. And then, of course, the pi's absorbed. So you have 1/2 less than or equal to x over 6 less than or equal to 3/2. And now, of course, you just want to isolate the x, right? So multiply by 6. This is just very basic, but what you do in trig when you're just working with these functions that have asymptotes. So you'll get a 1/2 times the 6, which is 3. And then, of course, the 2 absorbs into the 6 to give you a 3. 3 times 3 is 9. So now the pieces will look like this with a length here of 6. Okay? So that's it. And these are all symmetric. So now you think you just do 3 to 9, and then you bump down another 3, but of course leaving out the 3 using the fact of the existence of vertical asymptotes, which now get shifted. Now we have asymptotes at 3, 9, 15, etc. But now you've got length of 6, so we can just do a -3 to 3, 3 to 9, and then do another 6, 9 to 15, and then you can do 15 to 21, and then 21 to 27, go on forever. So the idea here is that this doesn't have anything to do except with the construct that trig functions are continuous with their define. So if we change the coefficient here of x, we've noticed here, since pi over 6 is less than 1, between 0 and 1, we will expand the intervals in the domain. And we see that we've done that. Okay, so when you see some of these problems, you're not doing overly complicated arithmetic and trigonometry. It's very basic, but you have to keep thinking about what is the definition of continuity? How do I apply it? And this is an excellent example of that. Now, what I want to do, finish up with 2 problems. The first one is a kind of like a linchpin of calculus. And if you look in the notes, I give an example of how you could construct a proof of the intermediate value theorem. Again, what I'm doing there is showing you about using certain properties, the supremum property of the real numbers, and then of course you have to use some sequential ideas. And it's fairly straightforward, but again, I want first, before you look at that, I want you to think about how we just do a basic example. Now, what I've written up here is basically the intermediate value theorem. Basically, you have a continuous image of a connected set is connected. Well, is connected set is a connected set. So since I wrote it that way, so the continuous image of a connected set is a connected set. So, and that should not be a surprise, but it does require some proof. So if you have an interval, and when we say connected, ladies and gentlemen, we're meaning that the set is in one piece. And since the sets we work with in calculus 1 are intervals, we've just got an interval, just like you think of it. It's one piece. You know, if you picked up the interval, it'd be in one piece, you set it over here. And so if you've got a continuous function, the beauty of the intermediate value theorem, it's very important, is that it maps that interval into an interval in the range. Okay, so when you think about that, and this is the statement that I have formally, that I have here. The intermediate value theorem, at least stated in terms of not talking about connected, would say this: if f is continuous on a closed set, A to B, of course, where A is less than B, and f of A does not equal f of B, and K is some value in the range, okay, between f of A and f of B. Now, excuse me, here's something that's very important. You don't necessarily know anything about the function except it's continuous, so you don't know if f of A is bigger than f of B or whatever, so it doesn't matter. So when you construct a proof, as you'll see in the notes, you can just assume without loss of generality that one's bigger than the other. The main thing is that they're different, okay? And so if you've got the connected set being mapped into the connected set, a connected piece becomes a connected piece under a continuous map, continuous function. Then, if you have any element between f of A and f of B, there must be some element between A and B, we call it C, such that f of C equals K. Now, there could be more than one. We don't necessarily know that the function is 1-to-1 or whatever, but there's at least one. So this is a remarkable fact of a continuous function. And you will use this quite often as you continue in calculus and you work in engineering and other science courses, because it is a linchpin of calculus. When you took pre-calculus, you probably talked about the property, but you didn't understand it in terms of more refined properties. But the best way to get at least a better understanding is to look at examples like this. So here's what we have. We have a function, and this is a nice problem, and it's very straightforward. We have a function x squared plus x divided by x minus 2, and it is given to be continuous on the set 9/2, or if you like, 4.5 to 6. Okay, and what I've asked here is to prove there is C between 9/2 and 6, such that f of C equals 10. So first, we have to look at the statement of the theorem and figure out, the f of A and the f of B, and then say, oh yeah, 10 is between those two numbers. So first and foremost, this function is defined on this set. Okay, so we're done with that. So it's automatically continuous. What kind of function is this? It's a rational function. You probably thought about that when we started. So when you look at this, you say functions that are rational, again, trigonometric, radical, polynomial, they are continuous where they're defined. So now what we want to do is just see what these values are. Okay, show that they're different and maybe show that 10 is between them. So we have f of 9/2. So I just did a little factoring here. This is very simple. So we have 9/2 squared plus 9/2 divided by 9/2 minus 4/2. I just wrote 2 as 4/2. Okay, now of course, 4 from 9 is 5. We get 5/2. And of course, I factored here because everything is easier when you factor. So you have 9/2 times 9/2 plus 1. Of course, 2 over 2 is 1. So that gives us 11 over 2. Here now, of course, the 2's absorbed. And so we have what? 99 divided by 10, which is 9 and 9 over 10. Okay, now f of 6, a little bit easier, no fractions. So we have 6 times 6 plus 1, just factoring from the onset, and then 6 minus 2. So we have 6 times 7 divided by 4. Okay, of course, 6 is 3 times 2, and times 7, and 4 is 2 times 2. The 2's absorbed. And so we have 21 over 2, which is 10 and 1/2. So now we're good. 10 is between 9 and 9 over 10 and 10 and 1/2. So that's really kind of important. Again, how do we know we can move forward with this? We have a continuous function on this closed set, and we have a value 10 that is between f of 9/2 and f of 6. And so by the intermediate value theorem, there is a C between 9/2 and 6 such that f of C equals 10. Now, when you think about this, you're thinking this theorem doesn't say, here's how you find C. Okay, it's not an algorithm that says do this routine and C is there. This is simply what we call in mathematics an existence theorem. Okay, you might think, okay, well, this number exists. So for instance, if you're dealing with polynomial theory of equation, and you've got a really odd zero, you can use the intermediate value theorem to isolate the existence of a zero, and then you can refine the approximation of the zero using certain routines. And we're going to learn how to do some of these. One that's very famous is called Newton's method. But there are many routines that you can use in numerical analysis to refine the approximation of certain numbers. So don't think that in general you will be able to do what we're doing here. This problem has a nice solution, but in most cases, we simply know that we have the existence of a number, and then we can move the problem forward because we know we're not just out blindly looking for something. We know it exists, and then we can refine our techniques to say, okay, well, it's in this interval, so let's work on this and see if by some numerical method we can maybe produce it to 3 or 4 decimal places. Maybe that's all we need. Okay, so now we just simply use the functional equation, replace x with c. This is a very simple equation. Set it equal to 10 and just solve it. Okay, so now we have c squared plus c over c minus 2 is equal to 10. So now you can just cross multiply. So you have 10c minus 20, c squared plus c on the left-hand side. So, you know, don't we wish all equations were this simple? When you transpose, you get c squared minus 9c plus 20. And of course, by AC method, you can use a -4 and a -5. My college algebra students and pre-cal students would appreciate this, but they know I always challenge them more than this. And so now you see that by zero product, you have a 4 or a 5. But again, of course, you know, maybe both of these work. Well, we know we should get at least one to work. So 5 is the one we have to choose because it's actually in the interval, 4.5 to 6. So now what we say, we take c equal to 5, and we actually have the element in the domain that maps into 10. So just remember, in general, the intermediate value theorem, again, the continuous image of a connected set is connected, is an existence theorem. And it's very valuable. You might be dealing with some really odd, beautiful functions, and you test some values. And if you can get an alternation in sign and you've got a continuous function, then you know you've got at least one zero. So that's really what's nice about the intermediate value theorem, especially working with certain functions. The alternation in sign would necessarily mean that the function would have to have at least one zero in that interval. So it's very powerful. So I guess I don't know what kind of math we did when we were not doing calculus. We certainly need the calculus to improve our techniques. Now, the very last one I thought was fun. It's right from your homework, and easy, but it just rings into the conjugate method, which is what I started out teaching you in the very first lecture. Simple, but a good problem. I think you'll like Cengage. The Larson text is one of the best calculus texts that I know of, and it's a complete text. And here's an interesting problem. So notice we have r greater than 0, a positive real number that's fixed, so it's a constant. And then we have this function, f of x, which is the square root of x plus r squared minus r divided by x. Okay, so here's what the problem says. It says compute the domain and then define f at 0 so that the function has continuity at 0. Okay, so you're like, all right, well, maybe we have a function with a hole in it. I don't know. So when we look at the domain, we're just back to college algebra. We have to obey the radical here. So the x plus r squared must be non-negative. And then, of course, we can't divide by 0. So that's the easy part. Well, this inequality is trivial since r squared is a constant. So x must just be greater than or equal to the additive inverse of r squared. So again, at first, when I looked at this, I thought that the majority of the problem is down here. So now you can see that x can be greater than or equal to the additive inverse of r squared, which is a negative number, but we have to kick out 0. Anything bigger than the additive inverse of r squared, including it, that excludes 0. So there's your domain. So that was simple. Now, for continuity at 0, what we would need to do is show that we have a function with a hole in it. So now, if you look where we have 0 here, you just basically have r minus r over 0 or 0 over 0. So basically, I could just write this. This is indeterminate, okay? Indeterminate. So that's good. We know that there's hope. I mean, if we just have a 0 downstairs that's not upstairs, then that means the function's becoming infinite and we're done. We can't do anything. So using the same technique as before, we just multiply and divide by the conjugate. So we have the plus here. Now, of course, when you think of the outer and the inner, they absorb, and you've got x plus r squared minus r squared. And of course, now the r squared is absorbed, and you're just left with an x. And downstairs, you just have x times the quantity x plus r squared to the 1/2 plus r. So now notice, again, when the r squared is absorbed, you have the x's that absorb. And so you're left with a function that's actually defined as 0. This is what? What do I call this? This is the replacement theorem. Replacement theorem, such a wonderful result. It's just the utilization of what? Identities. What's an identity? An equation that is true for all values of the variables for which it is defined, okay? So now we can take the limit by direct substitution. So we just get the 0 here, so that gives us r squared to the 1/2. Well, of course, that's by definition the absolute value of r, but r is positive here, so that's just r. So we just get 1/2r. So yeah, 1/2r is how we can basically define the value of the function at 0. So define f of 0 to be 1/2r. Now, I hope these examples have given you some strategies as to how you should deal with the concept of continuity. It's not overly difficult, okay, because you understand limits, but you can always go back and do more work with limits. You can always go back and think more about the intermediate value theorem, but just remember the definition of continuity. And when you're dealing with a function in pieces, you just want to look at the transitions. You want to look at the transitions between the pieces. And however complicated that is, kind of drives what you need to do to figure out, for instance, how to make a function continuous on the entire real line, or how just to repair a function. So when we look at this, ladies and gentlemen, we see that we have a what? Removable discontinuity. Remember, with the removable discontinuity, you have the existence of the limit, okay? The greatest integer function was a train wreck, okay? It has infinitely many discontinuities. One good thing about that function is it's an excellent example where you have a countable number it's infinite, but it's also countable because all of the discontinuities occur at what? Integers. All right. So as a good example, if you're talking or discussing math with your friends, it's always interesting to bring up when people are asking you, well, you know, this function has this many discontinuities or whatever. We think of what was the problem with the secant, the way it was set up. Think about that. How would you classify those discontinuities? Well, of course, you would say they're infinitely many of them. And then again, the way the structure is set up, when you think about the integer endpoints and all, again, is countable. Okay, so what we mean when we talk about levels of infinity, we might mean something that goes on at infinitum, but we can mark them all. We say, you know, there's a way to move through these. We can just list them. We can list the discontinuities. Now, as we get more and more advanced, we might be thinking, can we have functions that are really, really messed up with continuity, having an uncountable number of discontinuities? That can blow your mind. So basically what we have talked about today are functions that have a finite number of discontinuities or possibly no discontinuities or a countable number of discontinuities. So use these examples thinking about removable, non-removable, the greatest integer function as non-removable discontinuities, and then thinking about the definition of continuity. So what you're going to find is that these concepts really bring together the idea of limit and kind of push your understanding to a higher level. So I hope you enjoy working on these examples because this is a fun topic. Now, the next topic for this week will be infinite limits. So those are really, that's even worse than a discontinuity. I mean, you remember we talked about the example where you had the existence of the vertical asymptote where you have a function becoming unbounded. So we're gonna focus on that and see how we analyze the behavior, and we're gonna call the phenomenon infinite limit, which makes no sense really because the limit's a real number. But we're going to use that characterization to say, okay, the function does have a behavior and we can understand it. It diverges to what? Positive infinity, or it diverges to negative infinity. So we want to address that and see what kind of arithmetic exists there and see how we can actually analyze those in ways that will complement what you did in college algebra and pre-cal when you did the rational function graphs, okay? So we're done with the discussion today, and good luck as you continue to study. Calculus is exciting, and we've got a lot to go, but I will always be here to support you. So see you later.